Welcome to Maths with EJD. In this video, I feel the need to revisit the idea of ordinary points and, of course, singular points in the next video. Of course, they are the basis for series solution to ordinary differential equations. So I feel I should talk about more clear ways of establishing that a given point is actually an ordinary point and a singular point that I'll be talking about in the next video. So these are very special concepts as far as series solutions for ordinary differential equations are concerned. So for starters, since you're dealing with ordinary points here, which I talked about it when I did an overview on series solution to ordinary differential equations. But here I want to give specific and clear ways for you to prove or to show that certain points are ordinary points. So an ordinary point, an ordinary point, an ordinary point of a second order linear differential equation, usually given as px y prime prime plus q of x, p of x y prime prime, q of x y prime plus r of x y equals 0. So an ordinary point of that kind of equation is actually a point. It is a point x equals x naught where the coefficients p of x, q of x, and r of x are analytic. I think I said that much previously. They're analytic. What that simply means is that they actually have Taylor series expansions. They have Taylor series expansions, basically, or they can be expressed as series that converge, basically. And we also know that P of X naught is equal to 0. Is not equal to 0, rather. P of X naught is not equal to 0, you know. So P of X, all those functions can be expressed as Taylor series, and then evaluating at P of X, you don't get 0. All right, because because if P of X is 0, for instance, the second order is gone, right? So um with that said, you should also know that at an ordinary point, at an ordinary point, okay, solutions solutions can be expressed solutions can be expressed as power series power series. We have seen this already. I mean, we did a detailed work on this. So power series summation from n equals 0 to infinity, or then you have an into x minus x naught raised to power n. So this is the kind of solution we get for this kind of situation. Okay, so let's look at some examples, which is actually the purpose why I brought this up again, to actually verify for sure that this is actually a power series. I mean, this is actually um we have ordinary points basically. Okay, example, consider consider the equation consider the equation y prime prime plus x y prime plus y equals 0. Okay, clearly, right? If you want to tackle this, we see that we can talk about step one, which is to want to identify. So identify p of x, q of x, and r of x. That's the first thing we want to do. So we say here, as you can see, right? If you compare here, you have y prime prime plus x y prime plus y equals 0. So if you compare this with the standard, which is p of x y prime prime plus q of x y prime plus r of x y equals 0. So it's clear, it's simply clear that p of x is equal to 1. All right. The coefficient of y prime prime here is 1. So p of x is 1. Then we also see that um q of x, q of x here is equal to is the coefficient of y prime, which is x in this situation, and then r of x is also equal to 1. Okay, r of x is 1. That's the coefficient of y. It's 1. So in all this case, now we see that all are polynomials. All are polynomials. Okay, hence Hence, analytic everywhere. Since they're polynomials, they're analytic everywhere. Okay? They're analytic everywhere. Of course, that's not all we have to say for that. That's so what we have done there is to check if those functions are analytic. The next thing we want to do, that's step 2. So in step 2, we want to check for ordinary points. So check for ordinary points. So if we check for ordinary points, then so again, you know that p of x is equal to 1 is not equal to 0. And one of the conditions is that p of x naught must not be equal to 0. Because if it is equal to 0, then the rule fails. So p of x is equal to 1, and it is not equal to 0 for all x. So we can say that thus every point x equals x naught is an ordinary point. Okay. So what you have to do, first of all, check if p of x, q of x, and r of x are all analytic. For polynomials like a constant number or something like x, they are analytic. But then for to check for ordinary points, you look at p of x. P of x is if p of x is if you evaluate maybe x equals 0 at p of x. All right, like if you put p of 0 here now, you get 1 always, and that is never equal to 0. So in that case, you can say that thus for every point x equals x naught, uh thus, every point x equals x naught is an ordinary point. Okay, that's what we do in this case. So, of course, we want to now go to the power series, which we did the other time. So let me just take that one slowly. So if we want to deal with this now, we can go for step 3, which I already did in depth. So I just want to take one example, just to for the sake of emphasis. So we now go for the power series solution, power series solution at x naught equals 0. Okay. So, of course, here we know that the power series is something like this. We assume that y is summation from n equals 0 to infinity, a n x raised power n. A n x raised power n because x naught is 0. So normally we should have a n x minus x naught all raised power n. But since x naught is 0, then we are going to have it this way. So then we can then do y prime with the first derivative. That would simply be summation from n equals 1 to infinity. Then we have n x raised power n minus 1, right? Then we go for y prime prime because the original equation is up to second order, so y prime prime. So we have y prime prime now is equal to, again, so that summation, since you have differentiated the second time, so it goes to n equals to infinity of n into n minus 1 x raised power n minus 2. Okay, so the next thing we do is to substitute. So substitute into the equation. So if you substitute into the equation, okay, I mean, want to write the equation again so we can follow carefully. So we have y prime prime plus x y prime plus y equals 0. Okay, so y prime prime is what we have up here. So that is summation from n equals to infinity of n into n minus 1. All right, x raised power n minus 2. And then for the next one now, we have plus x summation from n equals 1 to infinity of n into x raised power n minus 1. And lastly, we have y, which is summation from n equals 0 to infinity of an x raised power n. And all of this is equal to 0. So the next thing we need to do is to adjust indices, right? We adjust indices. In that case, we take it term by term. For instance, we start with the first term. So this is the first term now. And to adjust the indices, we want to basically take it back to where we have x raised power n. All right. And the way to do that is we need to move 2 steps back from 2. So that means we have summation from n equals 0 to infinity. And once we do that, it's going to affect every other thing. So for instance, it's going to change an to an plus 2. Okay. That'll be n plus 1, n plus 2. And then for n, it changes to n plus 2 also. And then for n minus 1, so we have n minus 1 plus 2. That'll be n plus 1. And then we have x raised power n. So no more n minus 2 up there. And then we go for the second term. For the second term now. Now, the second term, we need this place to be x raised power n. Interestingly, we have an x out here. So if you multiply x by that, it automatically adjusts that. So we don't have to touch any other thing. So in that case, we have summation still from n equals 1 to infinity of an, n, then x raised power n. So with the x multiplying that x inside, then we have that not shifting because this is basically shifted by x. So this is shifted by x, not by the normal movement we did for the first one. So with that, we have that in order. And then we have the third term. We have the third term. So the third term is just it's okay the way it is, right? So we've dealt with this, right? The third term is normal. We have x raised power n already, so we don't have to worry about it. So we just have summation from n equals 0 to infinity of an x raised power n. Okay, so that's okay. So the next thing we want to do is to combine. So we now need to combine everything, because it's one expression, right? So we combine everything, and from by combining everything, what do we have? Okay. So we need to combine everything. Okay, I mean, let's just do what we need to do. So this is an plus 2 here, right? So we have an plus 2 into n plus 2 into n plus 1. Okay, that's for this first one. And from that now, okay, everything is plus, right? So the next thing is to have plus an n, okay? This an here. We also have this one. Okay. Um, but then this one is starting from n equals 1. This one starting from n equals 1. Okay. Okay, I think I get what we should be doing now. Let's be more careful in doing this. Now, for the sake of harmony, right? We have to take care that, this one here is starting from n equals 1. So we have to make up for that. So this is starting from n equals 1. So this and this are the same level. So we need to expand, we need to do this one in such a way that, okay, in fact, let me do it this way. So we have summation from n equals 0 to infinity for so we extract this stuff now. So we have n plus 2 into n plus 2 n plus 1. We have this. Then okay, x raised power n is common already, so let's leave that alone. So the next one we have summation from n equals 1, all right? N equals 1 to infinity of an, that's n. X raised power n is going to come out at the end of the day. Then plus summation from n equals 0 to infinity of an again. So all this now, all this, we have x raised to power n. Uh, I'm trying to see how best to put x. Just know that we have x raised to power n here. We won't be able to put it directly now. So I'll just hang it up here. So by the time I'm done with this next step, we can now easily factorize it out. Okay. So now, for everything to be at the same level, right? From everything to start from n equals 1. So it means we have to take care of n equals 0. So if you put n to be 0 now, it means that this part is just going to be a, because n is 0, right? So this is going to be a2 into 2 into 1. Okay, so an plus 2, that's a0 plus 2, that's a2. Then 0 plus 2 is 2. N plus 1, that's another 1. So we have that. Then so we now have that plus summation from n equals 1 to infinity of because we've taken that out, so we have an plus 2 now, n plus 2, n plus 1, x raised to power n. Okay, let's still keep that there. Then this one is already plus 1, so we can leave it. Summation from n equals 1 to infinity an n. Okay, and for here too, we need to take care of the 0 part. So for the 0 part here now, so we say when n is 0, so we just have a naught, a naught. Then we now have summation from n equals 1 to infinity of an x raised to power n. All right. So we have, of course, a0 x raised to power 0, which is 1. So we don't have to worry. Okay, we don't have to worry because x raised to power 0 is already 1. So we can now bring this out together. So this one and this one can come out together. So we now have 2a2 plus that a naught there, plus, so every other thing is now summation from n equals 1. Summation from n equals 1 to infinity, right, of then we can have um n plus 2, n plus 1, okay, an plus 2 there. So we can have we can have all of that covering everything. So this is from n equals 1. Then for here now, we have just an plus n, or rather n a sub n, right? And then we have just an here, and all of that x raised to power n equals 0. Okay, so this is what we have now. So things are tidier now. So with this, um okay, um since since coefficients, okay, let me just say coefficients must be 0, right? Coefficients must be 0 because the whole expression is equal to 0. That means that the coefficient must be 0. So if that is the case, so we now take it for, we say for n equals 0. So for n equals 0, this is just all we have. So we have 2a2 plus a naught is equal to 0. So what that simply means is that 2a2 is equal to minus a naught. If you divide through by 2, you have a2 is equal to minus, I can even say that is half a naught. That's half a naught. So this is our a2 now, based on what that expression gives. So that is for n equals 0. Then we can do the rest too. So we can say for n greater than or equal to 1, we can take care of the rest. So that means that everything here should be equal to 0, right? So that means we have n plus 2 into n plus 1, an plus 2 plus an plus an, right? Okay. Interestingly, an is common. So we have an into n plus 1 all together. An into, or better still, let's put the n plus 1 first. So we have n plus 1 into an, and this is equal to 0. Mind you, this is what I've just done. So these two now, these two, is like we have n an plus an. So that means that we have an is common into n plus 1. So that's n plus 1 an. That's what I brought down there. Okay, so that's better carefully done. Okay, so with this now we can then tidy things up. Interestingly, what we are looking for, we need recurrence expressions like this. So we can say that this is n plus 2, n plus 2. Well, first of all, n plus 1 can cancel out. Okay, we can divide through by n plus 1. Let me say that. Let me just say divide through by n plus 1. So if we divide through by n plus 1, we're saying this is n plus 2 into n plus 1, an plus 2 divided by n plus 1, because n plus 1 is on both sides. So we have n plus 1, an all over n plus 1, and that is equal to 0 all over n plus 1. Okay, so this just cancels this cancels this, and all of that will be 0. So we have n plus 2 into an plus 2 plus an is equal to, all of that is 0. So from here now we can write a recursion formula, a recursive relation, so to speak. And this is n plus 2, an plus 2 equals minus an. Okay, so that means that an plus 2 alone will be equal to minus 1 over n plus 2, minus 1 over n plus 2 an. So this is our another recursive relationship. Okay, so and this only holds for n greater than or equal to 1, because the one for 0 is already stated up there. So with this in place now, then we can get our recurrence relations. Okay, um okay, so this simply means that we already have a2, we have a naught. We don't seem to have a1. Can we have a1 somewhere? If n is equal to 1, we only go from n3. Okay, in short, it looks like we can only have 0, 2, 4, and so on, because of what this looks like. So let's go now and say we already know a2 to be minus a naught divided by 2 settled. Then the next thing we can get is a4. Okay, if we need a4, we have to use this. So this is for a2. We jump like that. So for a4 now, for a4, so it means n has to be 2. So that means for a4, n is equal to 2. So it means that we have a4, okay, to be equal to minus 1 over, since n is equal to 2, that's minus 1 over 4 a2, okay, a2. And interestingly, we already had a2 to be minus a naught over 2. So that means that a4 is equal to minus 1 over 4. A2 is minus 1 over 2 a naught, okay. So that means that a4 is equal to 1 over 8 a naught, okay. So a4 is done like that. So the next thing we want to get is, we can get a6, right? We can go for a6. So for a6, that means that n has to be equal to 4, based on what we have here, because 4 plus 2 will give us 6. So we have a6 is equal to minus 1 over, since n is equal to 4, so that will be 1 over 4 plus 2, 6. Then an, that will be simply a4. Interestingly, we have a4 up there. So this is a6 equals minus 1 over 6. A4 is 1 over 8, 1 over 8 a naught. Okay, so a6 is equal to minus 1 over 48 a naught. Okay, so we have that in place. All right, that's for the even parts of things now. Um, so now we can say, is there a way we can get a1 here? Can we get a1? Let me see. A2 is minus half a naught. Um, can we get, when n is when n is this is a naught. Okay. can we get this is an? What if we need what? Okay, good. If n is 1, I think we can get a1 somehow. Okay. So what if you're interested in a1? If n is 1, I mean, this is what works for 1, right? So, okay, let me just go for that. So we have for even values, right? For even numbers, we already have that. So let's try something for odd values. Okay. For, let me just change this. For odd, should I say coefficients? Is that the way to go? I think for odd coefficients, so we can say, uh, since this happens for n greater than or equal to 1, so we have an, we have an plus 2 equals minus 1 over n plus 2 an. Okay. Um, so we can have a relationship. So for n equals 1, okay, so that means we have a3 equals minus 1 over 5 a1. Okay, so I mean, this is a sweet relationship. This is established for a3. So we have this for a3 minus 1 over 5 a1. Okay, right? Because, oh, sorry, minus 1 over 3 a1, not 1 over 5. Because 1, so it's 1 minus 1 over 3. Sorry, this is because n is 1. So 1 plus 2 is 3. So that's minus 1 over 3 a1. Okay, that works. Okay, so that we say for n equals, so if you take n equals 2, 2 doesn't work because we've taken care of n equals 2 before. All right, so let's take for n equals 3. We have to jump. So even numbers together, odd numbers together. So that means we have a5 equals minus 1 over 5 a3. Interestingly, we have a3 there. So a5 is equal to minus 1 over 5. And a3 is minus 1 over 3 a1. Okay. So that means that a5 is equal to 1 over 15 a1. Okay. So now we have a1. Okay, we have a3 and a1 together. And then we have a5 this way. So at the end of the day, we can have uh s- so the overall solution, the overall solution would be the overall solution would be, you remember where we started from, y is equal to, the overall solution is such that y is summation from n equals 0 to infinity of an x raised to power n. That's where we started from. So if you can expand, so we have from n equals 0, so we have a naught x raised to power naught, x raised to power 0, right? Then a1 x raised to power 1 plus a2 x raised to power 2 plus a3 x raised to power 3 plus a4 x raised to power 4. I think we got up to a6, right? So we have a5 x raised to power 5 and a6 x raised to power 6 and so on and so forth. So we can just fix up all the values. So y equals, okay, well, we have something in terms of a naught. X raised to power 0 is 1. So this is just a naught plus a1 plus a1, right? Um, we have a1 in terms of, so we can just say that would just be a1x. You know, we have a naught and a1x. But a2 now, we now begin to have them in terms of a naught and a1. So what is a2 now? A2 is minus a naught over 2. Okay. So that's minus half a naught, then that's minus half a naught x squared. Okay, that's this now. Then for x3, for a3 rather, a3 we have minus 1 over 3 a1. So minus 1 over 3 a1 x cube. Okay, what about a4? A4 is a4 is 1 over 8 a naught. Okay, that's 1 over 8 a naught x raised to power 4. Okay, so we still have 2. So for a5 now, What is A5? A5 is 1 over 15 A1. That's 1 over 15 A1 x raised to power 5. X raised to power 5. And lastly, we have A6. A6 is A6 is minus 1 over 48 A naught. So we have minus 1 over 48 A naught. A naught x raised to power 6. Okay. So we can tidy things up like that. Of course, this continues, right? But we just stop here, So y now is equal to A naught. So let's just put all the knots together. So we have A naught, all right, minus 1 over 2 A naught x squared, okay, then plus 1 over 8 A naught x raised to power 4, and the rest continues like that. So that's for the A naughts. Then for the A ones, now we have plus A1x, okay. Then next we have minus 1 over 3 A1x cubed. Next we have plus 1 over 15 A1 x raised to power 5, and all of that also continue. So finally, we have y of x, right, equals, so if you factorize A naught, so we have A naught into we have A naught into 1 minus x squared over 2, okay, x squared over 2, then we have plus 1 over 8, plus 1 over 8 x raised to power 4, okay, plus all this. And then now plus A1, for this now, A1 into x minus x3 over 3 plus x raised to power 5 over 15, and all that and all that. So this is our solution to the problem. This is the final solution to the problem. So you can now see the A naught and A1 as the usual constants we have, from the standard method we've been using. Okay, so this is how we go. Okay, so it's more like we are revisiting the whole idea of power series method, and then how to clearly establish regular singular points. And as I always like to do, can we take some practice to be sure these points are clear? So practice uh, one, for the equation, for the equation y prime prime plus 2y prime plus y equals 0. Okay, for this equation, so A, verify that all points, are ordinary points. I think it's pretty much like what I did in the example. Verify that all points are ordinary points. Then B, just what I did now. Find a power series, solution centered at x equals 0. Okay, that's question 1. So question 2, consider 1 plus x squared y prime prime plus xy prime plus y equals 0. Okay, so A now, determine if x equals 0 is an ordinary point, B, compute the first 4 terms, compute the first 4 terms of a power series or a power series solution at x equals 0. So let's take it back to question 3. For y prime prime plus x squared y prime plus 3y. Is that pretty clear? Let me be sure. For y prime prime plus x squared y prime plus 3y equals 0. Okay. A now, identify all ordinary points. Identify all ordinary points. Okay. D, use a power series method. Use a power series method to find to find to find a solution at x equals 1 up to x cube terms. Okay. Yeah, let me see your answer in the comments, whether on Facebook or on YouTube. Okay. And of course, let me know in the comment section how helpful these videos are for you. And of course, if you like me to solve a question or teach on a particular topic, feel free to let me also know there. If you have subscribed, thank you. If you have not subscribed, please go ahead and subscribe because you have a lot more coming. In the next video, I'll be talking about singular points, and you don't want to miss that also. Hit the notification bell also so you can always get alerted each time a new video is released. And don't forget to like and share so that more and more people can have access to this great content. Before I come your way again, keep doing math right. Bye.